Welcome to Lesson 6 in our Exponential Functions unit. By this point, you should have finished the investigation for 1.5 on the exponential functions. If you haven't completed that, please do that before you continue on with this lesson. I know that the investigation may take more than one class period to do. Okay, we are going to summarize here how you know that a function is exponential by looking at the different models. For example, if you look at the equation of an exponential function, you know that it's going to be exponential if your independent variable, your x or your t for time or whatever it happens to be, is an exponent. So it's up in the exponent position. So I'll type that in here and give you a couple of examples. Okay, so for example, we could have y is equal to 2 to the exponent of x, where 2 is our base, but our independent variable, that x, is up in the air, it's the exponent. Or when we did our financial math, we might have said that the amount was equal to $100 to begin with, and then we had our growth of maybe 3% interest, so it's 1.03 to the exponent n. So n is our independent variable in this case, and n might be the number of years. So we're growing interest in those questions, which is exponential growth. All right, how do you know from a table of values? Well, you found out from your investigation that if the ratio of the first differences is a constant, and that it will be exponential, and that constant value is actually equal to the base. So from our table of values, that's how we know it's exponential. Okay, so the table of values, the ratios of the first differences in y are constant, and that constant value is equal to the base. Now, from a graph, we know a function is exponential if it has what I call a whoosh shape. Okay, and I think of it as the toboggan hill or the ski hill, and your whoosh, whoops, wrong pen. Let me grab my pen here. It is that you are whooshing down the ski hill. Okay, so what happens with our exponential growth is it's really steep on one end, and then it approaches what we call a horizontal asymptote. So as x approaches, in this case, positive infinity, our graph is approaching that horizontal asymptote. And of course, that whoosh graph could go the other way as well. We could start here and then end up growing this direction. But again, we have that horizontal asymptote, which is a line that our graph gets infinitely close to, but never in theory touches. All right, the last model, so we've talked about equation, we've talked about tables of values, we've talked about the graph, and then of course we've got the descriptive model. In the descriptive model, we have a percent growth or a percent decrease, or something is 2 times as large or increases by 200%. So those descriptions are what we're looking for to know that it's exponential. Okay, so you should make sure that you are aware of those various ways to tell that something is exponential. All right, we're going to move into the equation, the generic equation for an exponential function. I'm going to talk about that here. And just in general, we end up with a y equals, and then we use the parameters a and b, and then our independent variable, of course, is the x. And when we talk about this, we are always talking about x being the positive exponent. If you have the negative exponent as your, like a negative x, then you want to apply that -1, that negative exponent rule, to the base to change the value of the base so that the x then can become a positive value. And why we want to do that is so that we know if we're talking about growth or decay. So make sure that your x is positive. So take care of any negative exponent rules to change that into a positive x. Okay, make sure x is positive here. All right, now to begin with the a, what we have for a, the a is like the 100 up here. It's your initial amount, or it's also your y-intercept. So on the graph, it's the y-intercept, but in a word problem, it's the starting value, the initial amount that you are starting with. Okay, the initial value there. All right, the b, let me use a different color there. This only has a limited number of colors, unless of course I can find a way to figure out if there's more colors, and I have not. Whoops, I'm playing around with this while I'm talking, and I shouldn't. Let me just go ahead and pick. I'm trying to pick yellow, but it won't let me pick the yellow. There we go. Okay, change this to yellow, and in fact I'm going to go the other way with this. Okay, let me undo, and there we go. Okay, let's go here. So the B, of course, is the base, and the base indicates if it's growth or decay. So B for base indicates growth or decay. Growth or decay. Now, if that B value, and again, this is only if your X is a positive. If your B value is greater than 1, bigger than 1, then you've got growth. Okay, so we'll put in here growth if B is greater than 1. Okay, so that's a B is greater than 1. And remember the B, so B would be equal to 100% of the original value plus the percent that you're increasing by. So that's supposed to say increase. And I don't know whether there's exactly enough room there for you to actually see that. The decay means that your B value is between 0 and 1. Okay, so you have exponential growth, which means your graph increases if B is greater than 1. You have exponential decay, or decreasing, if B is between 0 and 1. Okay, so this is saying 0 is less than B is less than 1. And again, your B is equal to 100% to begin with, but this time because you're decaying, you're decreasing or subtracting the percent that you're decreasing by. Okay, so if you had bought a vehicle, because this is a common question, and that vehicle decreases by 15% each year, then what you're going to have is 100% of the value, and then you're subtracting the 15%. So 15%, remember, convert that to a decimal amount, and that gives you 0.15. So your base ends up being between 0 and 1, 0.85. But that's just an example there. You don't need to include that in your, I'm just going to erase it there. You don't need to include that in your note. All right, the other two things that I want to add to this is that B cannot equal 1, because you would have found that that gives you a horizontal line. And you also know that B can't be negative, because if you make your base negative, you just end up alternating back and forth above and below the x-axis, because it ends up being positive and negative values. And then you don't get that nice smooth whoosh curve. So that's the last thing I'm going to add to here, but I'm going to type it in because it's clearer. Okay, so I've just summarized those two things. B cannot equal 1, it gives a horizontal line, and that's because if you have y equals, let's see here, let's make that in green. If we had y equals 1 to the exponent of x, if you put any value in for x, no matter what value you put in, it'll always equal 1. And so it just gives you a horizontal line. And B cannot be negative, so it won't, because it won't give a smooth curve. The values will alternate between positive and negative values depending on whether the exponent is an even or an odd number. All right, so that concludes this part of the video. Continue on with the example here. It says write the following in the form y equals ab to the x, where x is a positive exponent. So each one of these has a negative exponent. Apply that negative exponent rule so that the x then becomes a positive exponent. And then you can identify if the function is increasing, so you have growth, or decreasing, which is your decay function.